Hi, so we're looking at Charles' law next. And in Charles' law, we're holding pressure and amount constant. And so we're going to look at the volume and the temperature relationship. So temperature has to do with the speed of the particles. Volume, obviously, is the space that those particles occupy. So we're going to look at our demo here, which is ivory soap in the microwave. So what we're going to do is we are going to take some ivory soap. Ivory soap has a very distinct odor to it. It is also unique in that it's pretty, has a low density. So I'm going to take some of this out here. And normally if you were to take a piece of ivory soap and put it in water, it does something weird, which it actually floats in water. Now, normal soap actually sinks. The reason why ivory soap floats is because it has a low density. And the reason it has such a low density is because it has air pockets inside. So it's actually, a lot less soap than, you would get with a regular soap bar. So a regular bar of soap would sink, but this stuff floats because of these air pockets. And so because it has air pockets, we can look at the relationship between the volume and the temperature here, because again, these are gas laws, so they only apply to gases. So what I'm going to do is I'm going to cut a piece of this ivory soap, and I'm going to put it in the microwave. So here's my piece. I'm just going to put it on a paper towel, and I will put it in the microwave here. I'm going to microwave it just for a minute. And so as my temperature goes up, my particles are going to start moving faster. And if my amount is the same and my pressure is the same, meaning it should have the same amount of collisions, then what should happen to the volume? Well, if my particles are moving faster, they're going to need more room to move. So let's see if it is changing. I don't know if you're able to tell at all in the camera, but I'll take it out for you in a second to show you. Okay, it's been going for about 40 seconds. And this is what it looks like. So these air pockets expanded because I increased the temperature, so the particles are moving much faster, so they need more room to expand. So it's kind of fluffy. All right, so it looks like this is the direct relationship between the temperature and the volume. And so in words, we'd say the volume of a fixed quantity of gas at constant pressure increases as the temperature increases. Or you can say at constant pressure and amount, the volume of a gas is directly related to the temperature. In terms of a math formula or an equation, V is proportional to T because they're directly related. So I can remove the proportionality symbol and put an equal sign and a constant. So V is equal to K times T. Or I can rearrange it to say V over T is equal to K. If I measure the volume and the temperature initially and say V1 over T1 is equal to K, and then I measure it after I've heated it, V2 over T2, that would also be equal to K. So I can set V1 over T1 equals V2 over T2. Since both of them are equal to a constant. Just so you know, you can always rewrite this as well. So you can write it as T1 over T2 is equal to V1 over V2. That is also a direct relationship. Or you can even write it as, let's say T1 over V1 equals T2 over V2. So there's no reason why the V's are on top and the T's are on the bottom. You can switch them. You can put the T's on top and the V's on the bottom. As long as 1 and 1 go together and 2 and 2 go together. Or you can do 1 and 2 and then 1 and 2. Any of these three versions would work. They are all a direct relationship. You also need to know what it looks like in terms of graphical analysis. So if you were to graph volume versus temperature, you would get a linear relationship here. And if this was the Celsius temperature, you would get 0 volume at negative 273 Kelvin, or sorry, negative 273 Celsius, which is absolute zero, right? So this is one of the ways they were actually able to calculate absolute zero, is by extrapolating. So they'd get data points for different gases, and they would extrapolate and see where it would hit 0 volume, and that's when it would be the coldest temperature possible. And then finally, you need to be able to do an example. So let's do this one together. It says a gas occupies 14 liters at 275 Kelvin. What is the new volume if the temperature changed to 297 Kelvin? So this is a volume. This is a temperature. What is the new volume? So it looks like these were ones. They go together. This is V2. That's what we're looking for. And this is T2. So you're going to say, oh, this is Charles' law of volume and temperature. So it's a direct relationship. So V1 over T1 equals V2 over T2. V1 is 14 liters. T1 is 275 Kelvin. V2 is what we're solving for, and T2 is 297 Kelvin. So to solve for V2, you're going to take, you're going to cross multiply. So you're going to say 14 times 297 over 275. And for temperature, you have to use kelvins. For volume, you can use whatever units, but V1 and V2 are going to be the same units. They have to match. Before you put it in your calculator, make sure that your answer makes sense. So it looks like my temperature is increasing by just a little bit. What would happen to your volume? Well, it should increase just by a little bit as well, because it's a direct relationship. So when you punch it into your calculator, you get that V2 is equal to 15 liters.